네, 네, 여러분 안녕하세요. 네, 계속해서 수업을 좀 이어나가도록 하겠습니다. Okay, so let's start today's classes. So today we will more likely talk about this chemical potentials and some kind of example of how can you use that kind of chemical potential for some calculation. So before that, I will start with some kind of the rules of combining of the first and second laws. So this is the one of the concept which is related to this thermodynamic second law. But I just put this chapter here because this is quite closely related to this today's the content. So we will start from this thermodynamic first law. So the fundamental equation, the fundamental equation, which is the combination of the first and second law, is an expression for the change in internal energy that accompanies change in the volume and entropy of a system. So up to now, we have talked about this kind of internal energy change, and now we also know the entropy change. And here we will combine these two things in a single forms of equation. So I will talk conclusion first. So we will get this equation, which is the du, the internal energy change, equal to T ds minus P dV. So why this can be possible? Because the, how can I say, so from this the meaning of this internal energy, so we can start to list du equal dq plus dw. Yeah, so you know this one. This is the thermodynamics first law. And for the reversible the process and without known expansion work, so we learned that this the wref is the minus pdv. So that's why we put. So we learned this one is now in our previous chapters. So we can just put this one is the minus pdv. And also for the reversible changes, so we can have this one, so TDS, right? So we also run this in our previous chapters. So I'll show this one. Yeah, so in the chapter 3, we learned that things, so not have this classes. So anyway, so from the kind of fundamental laws, so we can just put that things here, and then finally we have this the final forms, du equal tds minus pdv. Right. And also, so this is a quite useful things. So because this is containing this entropy terms, also this volumetric terms. So we call this one is the combining of the first and second law. And because this du is an exact differential, so each value is independent of path. So you don't know. I mean. You don't put so many meaning on this one. So anyway, you can just think about this is the independent of path, right? So the fundamental equation applies to any change because it's the first. I mean, so what this means? Independent path is the state function, right? So we have learned this one also through our classes. So so this fundamental equation can be applied to any change of a closed system which doesn't have any additional work. I mean, non-expansion work. So if there is only the expansion work, then we can apply this equation, right? So we will rather further enlarge this concept to some kind of Maxwell relation. So I don't let you know the understand all this kind of mathematical situation, but just this is just for your information. So there's some mathematical approach because if there is a function of x and y, and this function can be shown as this df equal g dx and h dy, and this g and h are function of x, y. Then if it is the exact differential, then this has this kind of relation, which is the round x over round g and at the constant x, right? And round x over round h at constant y, and this is the same. So we call this kind of relation as the Maxwell relation. So using this Maxwell relation, we will derive our the thermodynamic relation. So we have this kind of first and second law combination, which is the du equal TdS minus PdV, right? So this is so you can see this is the xy, right? So like this one. This is the FSV, right? So du equal TdS, this one, plus minus PdV, this one. So this one is the same form of this equation. So because this one is the exact differential, then we can simply round v over round t, right, at the constant s equal minus round s over round p at constant v. So because of this Maxwell relations, we can get this functions equation. So using this kind of system, we can derive this kind of different types of Maxwell relation, which this is what we derived now. And from this Helmholtz energy, from this enthalpy, we get this relation. And from this, how can I say, this Helmholtz energy, then we have this one. And from this Gibbs energy, we have this one. So this is the kind of Maxwell relation. Thermodynamics equation, which is the derived, the organized by this Maxwell relations. So so the reason that I'm doing this one is not you understand about this the Maxwell relations, but I just because we will use this kind of equation in our next slide. So for your understanding, I just put this kind of process, but I don't want you study all these kinds of mathematical things. Yeah, but just because to avoid any kind of embarrassing situation of you in the next slide. So I put this kind of some detailed process for your understanding. Okay, so we have learned about this kind of fundamental equation from this the internal energy, and now we will derive some similar things for this Gibbs free energy. So we will drive this Gibbs free energy from this Gibbs free energy to this Maxwell relations. And why we should do this is because the variation of the Gibbs energy of system suggests that it is best regarded as a function of pressure and temperature. So what this means? So Gibbs energy is the function of pressure and temperature. So if we kind of have some kind of relations about this pressure and temperature, and then we can express this Gibbs energy depending on this pressure and temperature, and then we can understand about the kind of systems reaction. So the Gibbs energy of a substance decrease with the temperature and increase with the pressure. Why? We will learn in here. And the variation of Gibbs energy with temperature is related to this enthalpy by this Gibbs energy, but we will not cover these two things. We only cover this one. Okay, so let's see. So general consideration. So the fundamental equation of chemical thermodynamics for DG is the VdP minus STT. This is the conclusion. So how we can get this equation? First, now we know G equal H minus Ts, right? So dG equal dH minus dTs, right? So this can be dH minus TdS minus SDT, right? And because this H equal to U plus PV, so dH equal du plus dPV, right? And du plus, so that's why we can make this one as the du plus PdV plus VdP, right? So you can simply put this one in here. Then we get this dG equal du plus PdV plus VdP plus minus TdS minus SDT, right? But in our previous slide, we learned that du equal TdS minus PdV, right? So we can simply put this one here. Then we get this dG equal TdS minus PdV, right? This one. And PdV plus PdV and plus VdP minus TdS minus SDT, right? Then just simply remove this one and this one and this one, and finally we get this VdP minus SDT. So we get this equation as a dG equal VdP minus SDT. Okay, so now we get this final function of dG on this temperature and pressure, right? Then at this, how can I say, at constant pressure, then dP will be 0, right? Then we get this round T over round G constant pressure will be minus S, right? And in a similar way, at this constant temperature, then this will be 0. Then round P over round G at constant temperature is V. So that's why the Gibbs energy always decreases when the temperature is raised, right? Because this is kind of a slope of this temperature and Gibbs energy, and this slope is the minus. So that's why this Gibbs energy have inverse relation to this temperature. So that's why, so we can get this two-dimensional graph. It's a temperature increase and Gibbs energy is decrease. And depending on the phases, so gas is usually more sensitive to the temperature than each liquid or solid phases, right? So what this means? The kind of random distribution degree of a gas molecule is the larger than the liquids, which is the more closely related to this temperature. And for this the pressure, so here, so the Gibbs energy always increase when the pressure of a system is increased, because so you can see from that here, right? Because this is the slope of pressure over Gibbs energy is the positive, so that's why the Gibbs energy always increase when the pressure of the system is increased. And also Gibbs energy of gas is also more sensitive to the pressure than each liquid or solid phase. So this is quite common. I mean, it's understandable because the we can simply know that the gas can be will have a more freedom at the high temperature compared to this liquid or liquid or the solid. Okay, so until now we have talked about this relation between this pressure and temperature and internal energy and also the Gibbs energy. So with this one, we will go over to this thermodynamic aspect of phase transition. Yeah. So in the previous classes, we have learned about this chemical potential. And here, we will a little bit learn about this chemical potential. So the chemical potential of a substance decrease with increasing temperature at a rate determined by its molar entropy. Right? And the chemical potential of a substance increase with the increasing pressure at a rate determined by its molar volume. Right? And when pressure is applied to a condensed phase and its vapor pressure is rises. Okay, so this kind of so we will actually, this is the all what we will learn today actually. So because the we will talk about how this kind of definition can be satisfied from this thermodynamic equations. So in our previous classes, in our previous slide, we have learned about this relation. It's a dg equal vdp minus sdt, right? And they have these relations for the round T over round G at constant pressure is D minus S, and round P over round G at constant temperature is D volume V. Right? So how can we combine this equation with this chemical potential? So simply, the chemical potential is the Gibbs energy, molar Gibbs energy. So simply we can replace this G as a chemical potential to see this molar value of entropy or molar value of volume, right? So that's why we replace this G as a chemical potential. Then we have round T over round mu at the constant pressure is minus Sm. So this is the molar entropy. So we can simply draw this kind of diagram. At this temperature is increase, then chemical potential is decreasing, right? Like this. And gas has the higher the dependence on this temperature compared to the liquid or solid. It's the same as our previous concept, right? So the kind of system also can be applied to this volume. So we have this same equation. So we just simply replace that this Gibbs energy with this chemical potential. Then we have molar volume of the system depending on the at a certain depending on the pressure. Right? So at this certain temperature, and depending on the pressure, there will be different potential and also different volume. So that things is the replacing this one. Okay, so let's solve about actually. So this in summary. So you have to just simply memorize, remember these two things, and these two things is derived from this equation. So using this one, we can solve some kind of a thermodynamic problem like this one. Okay, so I will give you the few minutes to solve this problem. So and then let's solve together. Okay, so let's solve together this one. This one. So the problem is assessing the effect of pressure P on the chemical potential mu. So how can you do that? So they calculate the effect on the chemical potential of ice and water, same component, same composition, but the different phases. And the condition is of increasing pressure. So this is pressure is a variable from 1 bar to 2 bar. And at temperature T at just 0 degrees C. What this mean? At the constant temperature. And the density of ice is the 0.917 gram per centimeter. And that of liquid of water is the 0.999 under this condition. So if we have this kind of condition, how can we calculate this effect of chemical potential under this kind of condition? Okay, so let's solve together. Okay, so from this one, right? We know that the change in the chemical potential, of incompressible substance when the pressure is changed by delta P, pressure is changed delta P at this constant temperature is the Vm. So that's why we can simply, the change of chemical potential can be, we can over here, Vm delta P. Right? So therefore, to answer this question, we need to know the molar volumes, which is the Vm, of the two phases of the water. Right? So if we know this molar volume, then we know this the pressure change. Then we can simply calculate this the chemical potential changes. So the kind of the molar volumes are obtained from the mass density law, and the molar mass is m. By using this equation, it's Vm equal molar mass over the density of molar mass. Right? So you can simply replace this Vm as the density of molar mass. Then finally we have delta mu equal density over molar mass and delta P. Right? And we know this ice, density of ice and density of liquid water. And molar mass of water is the 18.02 gram per mole. So in your kind of how can I say, the homework or exam, I will also provide this molar mass too. So you can simply use that kind of values. You don't need to memorize this molar mass of water. Okay, so anyway, so we have this value, and therefore simply delta mu of ice equal, because this is the density of ice is the 0.917 gram per centimeter. So we can simply transfer our unit like this, then this one here, and molar mass here, right? And delta P is the only 1 bar, right? 1 to 2 bar. So delta P is the 1 bar. And this is the 1.10 to 5 Pascal. So if we calculate this one, then we get this value, plus 1.97 joule per mole. So in case of water, delta mu equal the density 0.999. Also similarly, we put that value here. And the molar mass of water is the same as the ice because the two things have the same composition, right? And then also the pressure change is the same. And if we calculate these two things, and then they have 1.8 joule per mole. So the chemical potential change during this pressure is larger for this ice than the water. So what this means? So because this chemical potential is the molar Gibbs energy. So if there's the more the Gibbs energy changes, then that means the ice will be more the changes in terms of their phases in this kind of condition, which is especially the increasing pressures. So this is what they are saying. So we interpret the numerical result as follows. So the chemical potential of ice rises more sharply than of the water, right? Yeah. So 1.97, 1.8. So if they are initially in equilibrium at the 1 bar, ice and water and equilibrium, then there will be a tendency for the ice to melt at the 2 bar, right? Because the larger chemical potential means the more tendency to be transformed. So that's why if we have water and ice, and then if we increase the pressure, then ice will have more tendency to be melted. Yeah, so, okay, so I think we'd better stop this class here. And before start this class, I will give you a quick summary in Korean. 네, 그래서 지난 시간에 이어서 이 케미컬 포텐셜에 대해서 이제 조금 설명을 살펴보았고요. 그 케미컬 포텐셜에 대해서 이제 어떤 우리가 실제적인 문제를 풀거나 할 때 필요한 몇 가지 식들이 있었습니다. 네, 그런 것들이 기존에 이제 그 연력학 제1, 2법칙으로부터 유도가 되는 거였고요. 이제 그거를 이제 저희가 이제 예전에 안 했어가지고 그 부분을 이제 먼저 하고 넘어간 거예요. 그래서 du equal TDS - PDV 이렇게 이제 그 유도를 할 수가 있고요. 이거는 이제 요전 시간들에 했던 것들을 여러분 참조를 하시면 되고요. 이거를 바탕으로 해서 이런 맥살 관계식을 통해서 뭐 이러한 어떤 관계식이 있다. 네. 그렇게만 아시면 될 것 같고, 이거를 뭐 여러분이 뭐 이 맥스웨이 뭐 어떻게 돼야 되냐 뭐 이런 거를 아실 필요는 없어요. 아, 그냥 이런 관계식이 있구나 하는 그 정도만 아시고 넘어가시면 되고요. 네, 그래서 그래서 앞에 말씀드렸던 그 연력학자 1, 2법칙 합친 거에 의해서 이런 식으로 깁스 에너지도 우리가 나타낼 수 있다. 네, 이렇게 유도를 할 수가 있고, 그래서 이 유도된 식을 바탕으로 비교해 봤을 때 이런 식의 또 관계식을 우리가 얻을 수 있다. 네, 하는 것까지 우리가 배웠죠. 네. 그래서 요거를 바탕으로 지금 케미컬 포텐셜에 대해서 얘기할 건데, 이 케미컬 포텐셜이 결국 몰라 깁스 에너지 체인지잖아요. 그러니까 몰라 깁스 에너지를 케미컬 포텐셜이라고 얘기하는 거잖아요. 그래서 요 값을 우리가 이제 알았고 여기다가 이거를 케미컬 포텐셜을 바꿔주면 몰라 엔트로피 체인지, 몰라 볼륨 체인지 이것들을 우리가 계산을 해줄 수가 있다. 그렇게 된 거죠. 그러니까 뭐 제가 뭐 장황하게 설명을 했지만 뭐 결국은 요게 핵심이죠. 이렇게 해서 이렇게 할 수 있다. 그래서 결국 우리가 이런 문제를 풀었을 때 이런 식을 가지고 간단하게 이런 값들을 대입을 해서 케미컬 포텐셜을 얻을 수 있다. 근데 여기서 우리가 알아야 될 게 이 케미컬 포텐셜 차이를 딱 보고 이렇게 온도에서 올라갈 때 지금 아이스에 대한 케미컬 포텐셜 차이가 더 크기 때문에 케미컬 포텐셜 이런 이 조건 안에서는 얼음이 녹는 방향으로 흘러갈 가능성이 크다. 뭐 그런 거 우리가 판단할 수 있다 하는 걸 여러분 말씀드렸죠. 그래서 뭐 이런 식으로 진행이 된다는 걸 말씀드렸습니다. 네, 그럼 수고하셨고요. 일단 오늘은 여기서 수업을 마치도록 하겠습니다. 네, 수고하셨습니다.